Have you ever paused, perhaps late at night when the world has gone quiet, and wondered whether everything you think you know about reality is only the thinnest skin stretched over something far deeper? I mean, really wondered. Not just about stars and galaxies, but about space itself, about time, about the very stage on which existence appears to unfold. Because you see, for centuries we have assumed that space is simply there, a vast emptiness where things happen, and that time is a steady river carrying us from past to future. It feels obvious, almost comforting. You wake up, the clock ticks, the universe seems to sit patiently around you. And yet, when physicists began to look more closely, really closely, that calm picture started to crack. Our senses evolved to catch falling fruit and approaching footsteps, not to perceive the deep architecture of reality. Our instruments, marvelous as they are, still only skim the surface. And that's the thing. Perhaps space and time are not the fundamental ingredients we once believed them to be. Perhaps they are more like shadows on a wall, hints of a hidden machinery humming quietly beneath everything we see. What if the universe is not a container, but an outcome? What if space is not the stage, and time is not the clock, but both are emergent, like a melody arising from vibrations you cannot see? When you touch a table, it feels solid, yet we know it is mostly emptiness. In the same way, when you move through space and age through time, you may be moving through a kind of interface, a user-friendly display of something far more abstract and profound. And I suppose the real question is this: if space and time are not the bedrock of reality, then what lies beneath them, patiently waiting for us to notice? Before we go on, I'd like to ask you to subscribe to the channel and leave a like. My aim here is simple: to help you drift off to sleep while exploring the wonders of science. Where are you on the map? Let me know where you are in the world and what time it is in the comments. It's always fascinating to see who's joining us from all around the world. So let's continue. We have lived for so long with the idea that the universe has a birthday that it has become almost impossible to imagine reality any other way. A beginning feels natural to us. We begin our days when we wake. We begin our stories with a first sentence. We begin our lives with a breath. And so, when science told us that the universe began with the Big Bang, we accepted it not only because the evidence was compelling, but because the idea itself felt deeply human. A moment when everything started, a cosmic dawn, light from darkness, something from nothing. It resonates with the way our minds are shaped. But, well, you see, nature does not owe us emotional comfort. And when we slow down and look carefully at what the Big Bang actually represents in our theories, the story becomes far less tidy and far more intriguing. The Big Bang is often imagined as a violent explosion, a fireball erupting into empty space. Yet that picture is misleading at the deepest level. There was no empty space waiting patiently for the universe to arrive. Space itself was part of what came into being. Every location we now point to with coordinates was once compressed into an unimaginably hot and dense state. The expansion that followed was not matter flying outward from a central point, but the stretching of space everywhere at once. And this distinction matters because it quietly removes one of our intuitive anchors. If space itself emerged, then the Big Bang was not an event that happened somewhere. It was an event that happened everywhere. As we rewind the cosmic film using our equations, we find that the universe becomes hotter, denser, more uniform. Galaxies dissolve into plasma. Atoms cannot exist. Nuclei break apart. Eventually, even protons and neutrons lose their identity. Physics simplifies in a strange way, and for a time our theories work astonishingly well. They predict the abundance of light elements. They explain the faint microwave glow that fills the sky. They describe how tiny fluctuations grew into vast cosmic structures. This success is real and profound. But if we keep rewinding, pushing closer and closer to the supposed beginning, the equations begin to protest. Quantities shoot toward infinity. Curvature diverges. Time intervals shrink toward zero. And then the mathematics simply stops making sense. This breakdown is what we label a singularity. It sounds dramatic, almost mystical, but in practice, it is a confession. It is physics admitting that it no longer knows how to describe what is happening. A singularity is not necessarily a real feature of the universe. It is a sign that a theory has been stretched beyond its domain of validity. When classical physics predicted that electrons should spiral into atomic nuclei, it was not revealing a truth about atoms. It was revealing the need for quantum mechanics. In much the same way, the singularity at the Big Bang may be telling us not that time truly began, but that our description of time has reached its limit. For a long while, singularities were treated as unavoidable endpoints. General relativity, the theory that describes gravity as the curvature of spacetime, predicts them quite generically. Inside black holes, at the origin of the universe. And it was tempting to accept them as literal. Time begins here. End of discussion. But there is a quiet discomfort in that conclusion. Because time, unlike space, is not something we can point to. It is not an object. It is a relationship. It is the ordering of change. To say that time began is to say that there was a moment when there was no before. But a moment is already a temporal concept, and, that circularity is hard to ignore once you notice it. We sometimes say that asking what came before the Big Bang is meaningless, like asking what is north of the North Pole. It is a clever analogy, and perhaps even correct in some sense. But analogies can also lull us into complacency. The North Pole is a point on a sphere embedded in a larger space. Time, however, may not be so easily visualized. We do not know whether it curves back on itself, whether it emerges from something deeper, or whether it dissolves entirely under extreme conditions. Declaring a question meaningless can sometimes be an act of wisdom, but it can also be a way of protecting ourselves from ignorance. To address some of the puzzles left by the simple Big Bang picture, cosmologists introduce the idea of inflation, a fleeting epoch of extraordinary expansion, driven by a form of energy unlike anything we encounter today. Inflation explains why distant regions of the universe look nearly identical, despite having had no time to communicate. It explains why space appears almost perfectly flat. It explains why tiny quantum fluctuations were stretched to cosmic scales, seeding galaxies and clusters. In many ways, inflation feels like a master key. It unlocks several doors at once, and yet, inflation brings its own questions. It requires a specific set of initial conditions, a particular kind of field, a carefully balanced energy landscape. And when we ask why those conditions existed, why that field behaved as it did, we find ourselves once again at the edge of explanation. Inflation does not remove the need for an initial state. It merely relocates the mystery. The universe did not begin with the hot Big Bang, we say, but with inflation. And then we must ask, what began inflation? Thermodynamics deepens the unease. The second law tells us that entropy tends to increase. Disorder grows. This gives time its arrow, its directionality. The past is more ordered than the future. Memories point backward. Causes precede effects. The universe today is far more entropic than it was in its early stages. And remarkably, the Big Bang appears to have been in an extremely low entropy state. Not chaotic, not random, but exquisitely ordered. This is not what one would naively expect from a beginning. It is more like the start of a carefully arranged game than the aftermath of an explosion. Why was the early universe so special? Why did it begin in such a rare configuration? Thermodynamics can tell us what happens next, but it does not tell us why the starting point was chosen. It is as if we walked into a library where every book is perfectly aligned, every page uncreased, and instead of asking who arranged them, we simply marvel at how dust will eventually accumulate. Then there is energy. We often speak of the Big Bang as the creation of energy itself, but energy conservation is deeply woven into our theories. Energy can change form, matter into radiation, motion into heat, but it is not supposed to appear from nothing without explanation. Some cosmological models argue that the total energy of the universe may be zero, with positive energy balanced by negative gravitational energy. This is an elegant idea, and perhaps even correct, but elegance is not evidence. And even if the net energy is zero, we must still ask why there is something rather than nothing, why there is a structure capable of balancing anything at all. Quantum mechanics is sometimes invoked here, with talk of universes tunneling into existence from nothing. But nothing, in quantum theory, is not truly nothing. It is a vacuum with properties, laws, fluctuations, a sea of potential. And that sea must exist somewhere, or in some sense, for anything to happen within it. The question shifts again, deeper, quieter, but no less persistent. At some point, we are forced to confront the possibility that the Big Bang marks not the birth of reality, but the limit of a particular description. Our observations are bounded by horizons. Light can only travel so far in a finite time. Beyond a certain distance, regions of the universe recede from us faster than light due to the expansion of space. They are not forbidden, but they are unreachable. In the same way, looking backward in time, we encounter horizons of knowledge. The cosmic microwave background is one such horizon, the earliest light we can see. Before that, the universe was opaque to photons. But opacity is not emptiness. It is simply silence in one channel. So perhaps the Big Bang is best understood as an observational boundary, not an ontological one, a veil, not a wall. And this reframing matters, because it invites new kinds of questions. Instead of asking what happened at the beginning of time, we ask what kind of framework gives rise to time at all. Instead of searching for a first moment, we search for underlying principles, laws that do not live in time, but from which time emerges. Some approaches to quantum gravity hint at this. In certain models, time loses its fundamental status. The equations do not single out a preferred temporal direction. Dynamics becomes relational. Change is defined not with respect to an external clock, but through correlations between systems. In such a picture, time as we experience it is a macroscopic approximation, like temperature emerging from the motion of countless molecules. Real, useful, but not fundamental. If time can emerge, then perhaps the Big Bang was not the start of everything, but the point at which time, as a useful concept, crystallized. A transition from a regime where temporal language fails to one where it becomes meaningful. A phase change in the deep structure of reality. Just as ice has properties that liquid water does not, spacetime may have properties that its underlying substrate lacks, and I suppose this is where our intuition struggles the most. We are creatures of time. Our thoughts unfold sequentially. Our memories are ordered. Our lives have narratives. To imagine a reality without time feels like trying to imagine color without light. But difficulty is not impossibility. It is simply a sign that we are standing at the edge of familiar territory. The Big Bang, then, may be less like a birth and more like a doorway. Not a creation event, but an interface. On one side, a domain where our concepts of space and time apply. On the other, something deeper, quieter, perhaps governed by rules we have not yet learned to articulate. And once you allow that possibility, another question begins to form, almost uninvited. If time is emergent, if the Big Bang is a transition, then what about space? The vast expanse we take for granted, the arena in which everything seems to happen, could it too be a derived feature, a surface phenomenon, concealing a richer structure beneath? And if so, how much of what we call the universe is actually accessible to us, and how much lies forever beyond the reach of our light, just outside the map we have drawn so far? And so, standing at that edge where time itself begins to blur, our curiosity naturally drifts outward. If the beginning of time may be less of a beginning and more of a transition, then what of the arena in which all of this seems to unfold? Space. The vast, silent expanse we imagine stretching endlessly in all directions. The stage upon which galaxies spin, light travels, and history appears to take place. We treat space as obvious, as given, as the container of everything else. But perhaps, you see, that assumption is just as fragile as the idea of a first moment in time. From childhood, we learn to think spatially, up and down, near and far, here and there. Space feels immediate, tangible, almost intimate. You can stretch out your arm and feel distance directly. You can look across a room and know how far away the wall is. And when we extend that intuition to the cosmos, we imagine the universe as more of the same, only larger, much larger. A vast three-dimensional ocean sprinkled with islands of matter. But the universe we can actually observe is not the universe itself. It is a bubble carved out by the finite speed of light and the finite age of cosmic expansion. Every cosmic map we have ever drawn is constrained by a simple fact. Light takes time to travel. When we look at distant galaxies, we are not seeing them as they are now, but as they were long ago. The farther we look, the deeper into the past we peer. Eventually, we reach a limit, a distance beyond which light has not had enough time to reach us since the universe became transparent. This boundary is not marked by a wall or an edge. It is marked by silence. No signals arrive from beyond it, not because nothing exists there, but because information cannot cross that gap in the time available. This is what we call the observable universe, and the name itself can be misleading. It sounds definitive, as if it refers to everything that exists, but it does not. It refers only to everything that can currently communicate with us. Beyond that sphere, space may continue. Galaxies may cluster. Physics may unfold exactly as it does here, or it may not. We simply do not know. Our maps end not at the edge of existence, but at the edge of information. And, this distinction is subtle but profound. The boundary of observation is not the boundary of reality. It is more like the horizon at sea. When you stand on a beach and look out across the water, the ocean appears to end at a distant line. But you know, intellectually, that the sea continues far beyond what your eyes can reach. The horizon is not a physical barrier. It is a limit imposed by geometry and perspective. In much the same way, the cosmic horizon marks the limit of what we can see, not what is there. The expansion of the universe complicates this picture further. Space itself is stretching. Galaxies are not merely moving through space away from us. The space between us and them is growing. For sufficiently distant regions, this expansion carries them away faster than light can bridge the gap. Not because they are breaking any speed limit, but because the limit applies to motion through space, not to the expansion of space itself. Signals sent today from those regions will never reach us. They are causally disconnected from our future. And so, the observable universe is not a static sphere. It is a dynamic one, shaped by the history of expansion. Regions that were once observable slip beyond our horizon. Others remain forever out of reach. And this leads to a quietly unsettling realization. There may be vast portions of space that exist right now, at this very moment, that we will never know about, not because our instruments are insufficient, but because the structure of space-time itself prevents any exchange of information. When cosmologists speak of the size of the universe, they are often careful to specify whether they mean the observable part or the whole. The observable universe has a finite radius, but the universe as a whole may be much larger. It may even be infinite, or it may be finite, but unbounded, like the surface of a sphere extended into higher dimensions. The data we have does not decisively answer this question. Our measurements of curvature suggest that space is very nearly flat, but nearly is not exactly. A universe much larger than our observable patch would appear flat to us, just as a small patch of Earth appears flat to someone standing in a field. This raises an intriguing possibility. We may be living inside a local region, a cosmic neighborhood, with properties that are not representative of the whole. The laws of physics we infer may be local approximations. The values of fundamental constants we measure may vary elsewhere. The large-scale structure we map may be a fragment of a far grander pattern. And all of this could be true without contradicting a single observation we have made. Our dependence on light as a messenger further limits our view. Most of what we know about the universe comes from electromagnetic radiation. Visible light, radio waves, microwaves, X-rays. These signals interact with charged particles. They scatter, absorb, emit. But what if much of the universe does not interact electromagnetically at all? What if vast components of reality are effectively invisible to light? We already know that this is the case to some extent. Dark matter reveals itself only through its gravitational influence. It shapes galaxies and clusters, yet it neither emits nor absorbs light. We infer its presence indirectly, through the way stars move and light bends. Dark energy, even more mysterious, appears as a pressure driving the accelerated expansion of space. It does not clump. It does not shine. It simply is, filling space uniformly, influencing the fate of the cosmos, without ever announcing itself directly. And between galaxies, in the immense voids that stretch for millions of light years, space appears empty. But appearances can deceive. These regions are not truly nothing. They are threaded with fields, fluctuations, perhaps particles that do not couple to light. They may host forms of physics that are almost completely decoupled from our instruments. To us, they look like darkness. To reality, they may be richly structured. So when we look at a cosmic map, filled with glowing filaments of galaxies and dark gaps between them, we are seeing only the luminous skeleton of a much larger body. We are mapping the parts of the universe that speak our language, and that's the thing. Silence does not imply absence. It only implies that we have not learned how to listen. The Hubble limit is often described as the edge of the universe, but this is a misunderstanding. It is not an edge in space. It is an edge in time and communication. It marks the distance at which the expansion rate causes recession at the speed of light relative to us. Objects beyond this limit are not unreachable because they are too far away in space, but because space itself is changing too quickly between us and them. This reframes the very idea of cosmic boundaries. The universe may have no spatial edge at all, no wall, no border, no outer surface. Instead, it may be bounded only by what can influence what, a network of causal connections, constantly shifting as space expands. In such a universe, there is no privileged center. Every observer occupies the center of their own observable sphere. Every point sees itself surrounded by a horizon. This symmetry is both beautiful and humbling. It means that our view of the universe is not special. Other observers elsewhere would draw their own cosmic maps, centered on themselves, containing regions we can never see. Their skies would include galaxies forever hidden from us, and ours would include galaxies forever hidden from them. Reality, then, is not one shared panorama, but a mosaic of overlapping perspectives, each incomplete. At this point, one might ask whether it even makes sense to talk about the universe beyond observation. Is it scientific to speculate about regions we can never access? This is a fair question and a difficult one. Science thrives on testability. Yet cosmology, by its nature, pushes against the limits of what can be tested. We have only one universe to observe. We cannot rerun cosmic history. We cannot step outside the system. And yet, by studying patterns, symmetries, and consistency, we can infer possibilities that extend beyond direct measurement. The very success of our theories within the observable universe gives us some confidence in extrapolating them further. But confidence is not certainty, and it may be that the universe beyond our horizon obeys laws that are subtly, or even radically different. The constants we measure may drift. The dimensions we inhabit may change their character. Space itself may have layers we cannot perceive from within. This leads to a deeply unsettling but also exhilarating idea. We may not be embedded in the whole of space, but in a slice of it, a particular layer defined by the types of interactions we can experience. Our three-dimensional space may be an emergent surface, a projection of deeper degrees of freedom. What we call distance may be a derived concept, meaningful only within this layer. If so, then the apparent emptiness between galaxies could be misleading. It may not be empty space at all, but a region where the rules governing matter and light no longer apply in familiar ways. A boundary not of existence, but of interaction. Beyond it, physics may continue, but decoupled from us. And this possibility forces us to confront a subtle assumption we rarely question. That space is the fundamental container of reality. That everything that exists must exist somewhere, at some location, but perhaps location itself is emergent. Perhaps space is not the arena, but the outcome, a relational structure arising from deeper rules. Once that door opens, it becomes difficult to close, because if space is emergent, then its apparent vastness, its apparent continuity, its apparent emptiness may all be illusions at a certain scale. Useful illusions, reliable illusions, but illusions nonetheless. And that thought naturally draws us toward gravity, the force that tells space how to curve, the phenomenon that reveals that space is not rigid but responsive. General relativity describes this beautifully, showing us how matter and energy shape geometry, but it remains strangely silent on what geometry itself is made of. And so, gently, almost inevitably, our attention shifts. If space is not fundamental, if it bends and stretches and perhaps even dissolves under extreme conditions, then what is the substance of this cosmic fabric? What gives space its ability to curve, to expand, to transmit gravitational influence? Is it merely geometry, or is geometry itself an emergent description of something deeper still? And I suppose once we begin to ask that, we find ourselves stepping toward the next layer of the mystery, where space and time are no longer taken for granted, but treated as clues pointing beyond themselves. And so we arrive, almost without noticing, at the fabric itself. Space. Not as a backdrop, not as emptiness, but as something that can bend, stretch, ripple, and respond. We have already loosened our grip on the idea that space is infinite and absolute. Now we must loosen it further. Because once you accept that space has structure, that it participates in the dynamics of the universe, a deeper and more unsettling question emerges. What is this structure actually made of? General relativity gave us a profoundly different way of thinking about gravity, not as a force pulling objects together, but as geometry. Matter and energy tell space how to curve, and curved space tells matter how to move. It is an idea of astonishing elegance. A falling apple is not being pulled by an invisible hand. It is following the straightest possible path through a curved geometry. Planets do not orbit because they are tugged by the sun, but because space-time around the sun is warped, guiding their motion. Gravity, in this picture, is not something that exists within space. It is a property of space itself. And yet, you see, this beautiful description hides an odd silence. We are told how space behaves, but not what space is. We are given equations that describe curvature, but no explanation of the substance that curves. We compare space to a rubber sheet, stretched and distorted by heavy objects. But the metaphor breaks down the moment we ask what the rubber is made of. A rubber sheet has molecules. It has tension because of electromagnetic forces between atoms. Space, according to our best theory, has no such underlying description. We are invited to accept geometry as fundamental. But geometry, at least as we usually understand it, is a description of relationships. Distances, angles, volumes. It is a language, not a material. To say that gravity is geometry is a bit like saying that music is mathematics. True, in a sense, but incomplete. Music arises from vibrating strings, columns of air, resonant bodies. Mathematics describes it, but does not produce the sound. So, what is vibrating, what is resonating beneath space-time? This question becomes sharper when we consider how space responds to energy. Space expands, space contracts. Space can carry waves, gravitational waves, ripples in space-time itself travel across the universe, stretching and squeezing distances as they pass. These waves carry energy. They can heat detectors. They can do work. And anything that carries energy usually has degrees of freedom, something that can be excited, something that can store and transmit information. So what, precisely, is being excited when a gravitational wave passes? In everyday materials, elasticity comes from microstructure. A metal rod resists bending because of the arrangement of atoms and the forces between them. A fluid flows because its molecules can rearrange. If space-time has stiffness, if it resists curvature in some way and yields in others, that stiffness must come from somewhere. To simply declare space-time fundamental is to stop the inquiry just as it becomes most interesting. This unease deepens when we look at the extremes. At very small scales, quantum mechanics reigns. Particles fluctuate, fields jitter, nothing stays perfectly still. But space-time, as described by general relativity, is smooth and continuous. It can be curved gently or sharply, but it does not flicker. It does not fluctuate in the way quantum fields do. At least not in the classical theory. This mismatch is at the heart of the long-standing tension between gravity and quantum mechanics. Quantum field theory assumes a fixed space-time background. Fields live on space-time. They evolve in time. They interact at points in space. General relativity, on the other hand, tells us that space-time itself is dynamic. It responds to energy and momentum. There is no fixed stage. The stage is part of the play. And when we try to combine these perspectives, the mathematics resists. Infinities appear. Predictions lose meaning. The theories refuse to merge gracefully. This is not merely a technical problem. It is a conceptual one. We are trying to quantize something without knowing what it is. We treat space-time as if it were a field, like the electromagnetic field. But we have no evidence that it has the same kind of underlying structure. Perhaps space-time is not something that should be quantized directly. Perhaps it is more like temperature, a collective variable emerging from many microscopic degrees of freedom. Temperature feels fundamental. Hot and cold are immediate sensations. Yet we know that temperature is not a basic property of nature. It arises from the average motion of countless particles. At very small scales, temperature disappears as a meaningful concept. Individual molecules do not have temperatures. They have velocities. In the same way, space-time curvature may be a macroscopic description of something deeper, something discrete, something statistical. There are hints of this in black hole physics. When we study black holes using the tools of general relativity and quantum theory together, strange things happen. Black holes have entropy. They have temperature. They radiate. This is astonishing. A black hole, which classically is just a region of space-time, behaves like a thermodynamic object. And thermodynamics, wherever it appears, usually signals the presence of underlying microstates. Entropy counts possibilities. It measures how many microscopic configurations correspond to the same macroscopic appearance. If a black hole has entropy, then there must be something that can be counted, something hidden beneath the smooth geometry. Degrees of freedom associated not with matter inside the black hole, but with the space-time itself. This suggests, quietly but insistently, that space-time has an internal structure. And, once you accept that possibility, the entire picture shifts. Space-time stops being the stage and starts being the actor. Or perhaps more accurately, it becomes the visible surface of a deeper process. Curvature is no longer a primitive fact. It is a collective behavior. Gravity is no longer fundamental. It is emergent. In some approaches, space-time is built from networks of relations, nodes and links, information and connectivity. Distances arise from patterns of interaction. Geometry emerges from entanglement. In others, space-time is like a fluid, with equations of motion that resemble those of hydrodynamics, suggesting that general relativity is an effective theory, valid only at large scales, just as fluid dynamics breaks down at the scale of individual molecules. What is striking is that many of these ideas, developed independently, point in the same direction. Space-time is not fundamental. It is an approximation, a remarkably accurate one in most circumstances, but an approximation nonetheless. And if that is true, then the question, what is space-time made of, may be as misguided as asking what temperature is made of. The better question may be, what gives rise to space-time? We can also approach this from another angle. Gravity is unique among the interactions. It is universal. Everything with energy gravitates. There is no way to shield against gravity. This universality hints that gravity is not just another force, but a manifestation of something more general. Perhaps it is the way energy organizes information. Perhaps it is the response of an underlying system to disturbances. Einstein's equations relate geometry to energy and momentum. But they do not explain why this relationship exists. They state it. They codify it. They work. But they do not tell us why spacetime should care about energy at all. Why should mass curve space? Why should curvature guide motion? These are not answered by writing down equations, no matter how beautiful those equations are. We often mistake predictive power for understanding. General relativity predicts the precession of Mercury, the bending of light, the expansion of the universe, the existence of gravitational waves. It is spectacularly successful. But success does not imply completeness. We can predict how a river flows without knowing the molecular structure of water. We can describe the motion of clouds without understanding the quantum behavior of individual droplets. In the same way, we may be predicting the behavior of spacetime without knowing its essence. Consider again the metaphor of elasticity. Space appears elastic. It can be stretched by expansion. It can be compressed by gravity. It can oscillate. But elasticity is never fundamental. It always emerges from interactions at smaller scales. Springs are elastic because of atomic bonds. Rubber stretches because of polymer chains. If spacetime is elastic, then what are its chains? This question becomes unavoidable near singularities, inside black holes. At the supposed beginning of the universe, curvature grows without bound. Distances shrink to zero. Densities diverge. These infinities signal the breakdown of the elastic description. Just as fluid equations fail at a shock wave, space-time equations may fail where their underlying assumptions no longer hold. Something new must take over, and perhaps that something new does not look like space at all. Perhaps it does not have dimensions in the way we understand them. Perhaps locality itself breaks down. Points may no longer be meaningful. Distances may no longer be defined. What we experience as space could be a coarse-grained illusion, smoothing over a fundamentally non-spatial substrate. This idea is deeply counterintuitive. We rely on space to define separation, to define individuality, to define existence. Something exists if it exists somewhere. But this may be a habit of thought rather than a law of nature. At the most fundamental level, reality may be relational rather than spatial. Things may exist not by being located, but by being connected. If that is the case, then gravity as geometry is a macroscopic story. A translation of relational data into spatial language. Curvature encodes how relationships deviate from flatness. Motion encodes how patterns of connection evolve. Space is not the canvas, but the picture. This perspective also reframes the mystery of why gravity is so weak compared to other interactions. Perhaps it is weak because it is not fundamental. It may be an emergent effect, diluted by the many degrees of freedom from which it arises. Just as pressure is weak at the level of individual molecules, but powerful when many act together. And as we follow this line of thought, we begin to sense that space-time is not the ultimate layer of reality. It is a remarkably coherent, stable, and persistent structure, but one that may arise from something deeper, something that does not live in space or time, but gives rise to both. Once you take that step, another tension comes into focus. Quantum mechanics describes probabilities, superpositions, entanglement. It does not respect classical notions of locality. Particles influence one another instantaneously across distances in ways that defy spatial intuition, though not causality. General relativity, by contrast, is deeply local. It is built from smooth fields defined at points in space-time. These two visions of reality sit uneasily together. Perhaps the reason is that locality itself is emergent. At fundamental scales, there may be no notion of here and there. Entanglement may be more basic than distance. Space-time geometry may be a bookkeeping device that summarizes patterns of quantum correlation. If so, then trying to quantize space-time directly may be like trying to quantize a shadow instead of the object casting it. And so, Gently but persistently, we are led to a radical possibility. That space-time, with all its apparent solidity and vastness, is not the bedrock of existence. That it is a derived concept, arising from a deeper layer that does not resemble space or time at all. A layer governed by rules we are only beginning to glimpse. If that is true, then our next challenge is unavoidable. Quantum mechanics works extraordinarily well within spacetime, yet spacetime itself may not be fundamental. How then does quantum theory fit into this picture? Is it also emergent, or is it closer to the underlying substrate? And what happens when we try to describe quantum processes without assuming space and time is given? That question, quietly waiting in the background, draws us forward toward the next layer of the mystery, where the familiar laws of the quantum world begin to strain against the very arena they were built to inhabit. And so, having loosened our grip on space itself, we find that another tension has been quietly waiting for us all along. It has been there for more than a century, humming beneath every successful prediction, every elegant equation, every technological triumph. Two theories, each breathtakingly accurate within its own domain, yet profoundly uncomfortable in each other's presence. Quantum mechanics and general relativity. One governs the very small, the other rules the very large. And when we try to make them speak the same language, the conversation falls apart. Quantum mechanics is strange in a way that feels intimate. It speaks of probabilities rather than certainties, of particles that are also waves, of outcomes that exist only when observed. It tells us that nature, at its core, is not deterministic, but statistical. That the universe does not always decide what will happen until it happens. This is unsettling, yes, but it works. It works with astonishing precision. The devices in your pocket, the screens you look at, the clocks that guide satellites around Earth all rely on quantum rules. Within its domain, quantum mechanics has never been proven wrong. General relativity, by contrast, feels majestic and calm. It describes a smooth, continuous space-time where gravity emerges from curvature. It is deterministic. Given the distribution of energy and momentum, the geometry of space-time is fixed. Given the geometry, the motion of matter follows. There is no randomness here, no ambiguity, just geometry unfolding with mathematical inevitability. It too works. It predicts black holes, gravitational waves, the expansion of the universe. Its success is undeniable. And yet, these two pillars of modern physics do not fit together. Not merely awkwardly, but fundamentally. Quantum mechanics assumes a fixed background of space and time, a stage on which quantum fields fluctuate. Time, in quantum theory, is an external parameter. It ticks forward, absolute and unquestioned. The wave function evolves with respect to it, but general relativity tells us that time is not external at all. It is dynamic. It slows near massive objects. It stretches as the universe expands. It is part of the system, not a backdrop. So here we are, you see, with two descriptions of reality that are each incomplete in the presence of the other. Try to apply quantum rules to space-time itself, and infinities appear. Try to treat gravity as just another quantum field, and predictions lose meaning. The equations explode. And these are not small discrepancies. They are signs of deep conceptual conflict. This tension becomes impossible to ignore at extreme scales. Near the center of a black hole. Near the earliest moments of the universe. Places where space-time curvature becomes enormous and quantum effects cannot be neglected. These are the places where our theories should overlap, and instead, they contradict one another. For decades, the dominant approach has been to try to unify them directly, to quantize gravity, to write down a quantum version of space-time, to force general relativity into the mold that has worked so well for the other forces. This effort has produced remarkable mathematics, bold ideas, and partial successes, but it has not yet produced a complete, experimentally confirmed theory. And perhaps, that persistence itself should make us pause. Because it may be that the difficulty does not lie in technical complexity alone, It may lie in the assumption that these two theories are meant to be unified at the same level, that they are siblings rather than descendants of something deeper. Quantum mechanics may not be fundamental either. It may be a set of rules that emerges when we describe a deeper system from within spacetime. Its probabilities may reflect incomplete access to underlying information. Its wave functions may be effective descriptions rather than literal entities. In other words, quantum mechanics may not be the bottom layer, and general relativity may not be either. If that is true, then trying to merge them directly could be like trying to reconcile the rules of chess with the rules of traffic, without realizing that both are implemented on the same computer. They operate in different contexts. They use different abstractions. The conflict may not indicate that one is wrong, but that both are partial views of a larger structure. This is where the idea of a deeper framework begins to whisper, a layer of description that does not assume space or time from the outset, a kind of metaphysics, not metaphysics in the philosophical sense, but a physical framework that stands outside space-time, from which space-time itself emerges. In such a framework, time would not be a parameter, it would be a consequence. Space would not be a container, it would be a relational pattern. The laws we call quantum and gravitational would be approximations, valid when certain conditions are met, much like thermodynamics is valid when many particles are involved. There are hints that this may be the right direction. In some formulations of quantum gravity, time disappears entirely from the fundamental equations. The universe is described by constraints, not evolution. Change emerges only when subsystems are compared to one another. Clocks are not external. They are physical systems like any other. This is deeply unsettling. We are accustomed to thinking of time as the ultimate ordering principle. Without time, how can anything happen? But perhaps happening is not fundamental. Perhaps relations are. And what we experience as time is the way those relations are revealed from within the system. Quantum mechanics already nudges us in this direction. Entanglement connects particles in ways that ignore spatial separation. Two particles can share a state even when light cannot travel between them in time. Their properties are not independent. They are parts of a single description. This non-locality does not allow faster than light communication, but it does challenge the idea that space defines separateness. General relativity, in its own way, also challenges separateness. The geometry at one point in spacetime depends on the distribution of energy elsewhere. Nothing is isolated. Everything participates in a shared structure. Both theories, despite their differences, hint at a deeper connectedness. So perhaps the mistake is not that we have failed to unify quantum mechanics and gravity, but that we have assumed they are fundamental descriptions to begin with. Perhaps both are shadows cast by a deeper architecture. And shadows, however sharp, do not reveal the full shape of the object that casts them. If spacetime is emergent, then trying to write quantum equations on it may be like trying to describe ocean waves using the coordinates of a map drawn on ice. Useful in calm conditions, but misleading when the ice melts. At the deepest level, the concepts of here, now, before, and after may simply not apply. This reframes many of our puzzles. The infinities that appear when we quantize gravity may not be bugs, but features, warnings that we are using the wrong language. The failure to reconcile the two theories may be telling us that we are asking the wrong question. Instead of asking how to quantize spacetime, we might ask what spacetime is a manifestation of. Instead of asking how quantum fields evolve in time, we might ask how temporal ordering arises from timeless rules. Instead of forcing a marriage between quantum mechanics and general relativity, we might look for their common ancestor. And once you begin to think this way, another mystery becomes impossible to ignore. The quantum vacuum, the so-called empty space that is anything but empty. Fields fluctuating, energy appearing and disappearing, a restless sea beneath apparent stillness. Quantum mechanics insists that even in the absence of particles, something remains. But if space-time itself is emergent, then where does this quantum vacuum reside? What does it mean for fluctuations to occur if space and time are not fundamental? The vacuum, which we treat as the ground state of fields defined on space-time, may itself be an emergent concept, and beneath it, there may be something else entirely. This thought pulls us naturally toward the next layer of the story. If both space-time and quantum fields may be effective descriptions, then the idea of emptiness must be re-examined. The void between things. The nothingness we assume underlies everything. Perhaps it is not nothing at all, but a doorway, a hint of a deeper reservoir of structure and energy, waiting beneath the surface of what we call reality. And so our attention drifts, almost inevitably, toward the vacuum itself, to ask not what exists within space, but what space itself may be floating upon. And so we drift, almost inevitably, into the quietest place of all, the vacuum, the space between things, the emptiness we imagine when we strip the universe of matter, of light, of motion. It feels like the most basic concept we have. Nothing there, nothing happening, a backdrop waiting patiently to be filled. And yet, well, you see, this idea of emptiness may be one of the greatest illusions we have ever constructed. In classical physics, empty space was exactly that, a void, a stage with no actors. Remove all particles, and nothing remains. But quantum mechanics shattered that calm picture in a way that is both subtle and profound. Even when we remove every particle we can detect, even when temperature drops as close to absolute zero as nature allows, the vacuum refuses to sit still. Fields fluctuate, energy trembles, pairs of particles briefly appear and vanish. The vacuum seethes with activity, like a restless ocean beneath a glassy surface. This is not poetic exaggeration. It is a precise prediction of quantum field theory, confirmed again and again by experiment. The vacuum has structure. It has energy. It has measurable effects. The forces between particles are altered by vacuum fluctuations. Atomic energy levels shift. Casimir plates attract each other in perfect emptiness. The vacuum is not a passive nothing. It is an active participant. And yet, here is the tension. All of this restless activity is described as happening in space and time. Quantum fields are defined on space-time. Their fluctuations occur at points, over intervals. But we have just spent so long loosening our grip on space-time itself. If space and time are emergent, if they arise from deeper rules, then what exactly is the vacuum fluctuating within? Where does this sea of energy live? This question is rarely asked out loud, perhaps because it feels dangerous. The vacuum is already strange enough. To question its location feels like pulling on a thread that might unravel the whole tapestry. But pull we must, because the answer, whatever it is, cannot simply be space itself. That would be circular. The vacuum energy problem makes this unavoidable. When we calculate the energy of the quantum vacuum using our best theories, we get a number that is absurdly large. Larger than anything we observe in the universe. If this energy gravitated in the way general relativity suggests it should, space would curl up violently or tear itself apart. And yet, the universe looks calm. Expanding, yes, but gently. Something is off, by an enormous margin. We often phrase this as a fine-tuning problem. Why is the vacuum energy so small compared to what we expect? But perhaps that framing is backwards. Perhaps the mistake is assuming that vacuum energy, as calculated in quantum field theory, is a literal energy of space itself. Perhaps it is a bookkeeping artifact, a sign that we are describing something emergent as though it were fundamental. Think for a moment about sound. In a quiet room, you might say there is silence, but silence is not the absence of air. It is the absence of audible vibrations. The air molecules are still moving. They are still colliding. They are still warm. Silence is a description relative to our senses, not an absolute state. In the same way, the quantum vacuum may be silent only with respect to particles we can observe, while remaining dynamically rich at a deeper level. The vacuum, then, may not be empty space at all. It may be the lowest energy state of a deeper system. A ground state of something that does not live in space-time, but from which space-time itself emerges. The fluctuations we describe may be ripples on the surface of that deeper structure. translated into space-time language because that is the only language we have. This idea becomes especially compelling when we consider phase transitions. In many physical systems, what we perceive as empty is simply one phase among many. A magnet above its critical temperature appears disordered. No magnetization, nothing special. But below that temperature, structure emerges. Alignment appears. Properties change dramatically. The underlying system was always there. Only its behavior changed. Perhaps space-time itself is like that. Perhaps what we call the vacuum is not the absence of structure, but a particular phase of a deeper reality. A phase in which space, time, and quantum fields take on the forms we recognize. And perhaps under different conditions, different phases exist, with radically different properties. This perspective also casts new light on the idea of zero-point energy. In quantum mechanics, systems never truly come to rest. Even in their lowest energy state, they fluctuate. This is often described as a fundamental feature of nature, but it may instead reflect the fact that we are observing an effective description. The underlying system may be perfectly well defined, with no mysterious borrowing of energy from nothing. The mystery may arise only because we are looking at it through the lens of space-time. So when we say the vacuum has energy, we may really be saying that our space-time-based description cannot fully subtract the background structure from which it arises. The energy we calculate may not be energy in the usual sense, but a residue of our incomplete perspective. This becomes even more intriguing when we consider that different vacua may exist. In quantum field theory, the vacuum is not unique. Different configurations of fields can represent different ground states. Some may be metastable, some may decay. Transitions between vacua can release enormous energy. In cosmology, such transitions are invoked to explain inflation and the large-scale structure of the universe. But again, all of this is described within space-time. Vacua differ in their properties of space and time, expansion rates, particle masses, interaction strengths. If space-time itself is emergent, then these vacua may be more like surface states, each corresponding to a different way of projecting a deeper system into a space-time description. The vacuum, in this view, is not a thing. It is a relationship, a way the underlying system appears when observed from within a particular emergent layer, and that means it may serve as a gateway, a boundary between the familiar and the fundamental. This is where the idea of the vacuum as a portal becomes more than metaphor. If space-time is emergent, then transitions in the vacuum may correspond to transitions between different emergent regimes, different renderings of reality, different rule sets becoming active. The vacuum may not simply be the lowest energy state within a universe. It may be the interface through which universes connect to a deeper substrate. This does not mean necessarily that we can tunnel through the vacuum to somewhere else, or that hidden realms are waiting just beyond empty space. But it does suggest that the vacuum encodes information about the deeper structure of reality, information that we have not yet learned how to read. And, this is where humility becomes essential. We are attempting to describe the foundation of existence using concepts that themselves may be emergent. Energy, fields, space, time. These may be approximations, effective tools that work beautifully within their domain, but fail when we try to push them too far. The vacuum energy problem may not be a puzzle to be solved by clever cancellation. It may be a clue, a sign that we are misinterpreting what the vacuum is, that we are mistaking a shadow for the object casting it. If the vacuum is a manifestation of a deeper system, then asking where it is located may be the wrong question. It may not be located anywhere. Location may be something that emerges only once the vacuum condenses into space-time. The deeper layer may not have positions or distances at all. Only relationships. Only rules. This also reframes the idea of nothingness. We often ask why there is something rather than nothing. But perhaps nothingness is not a meaningful concept at the deepest level. Perhaps there has always been structure, always been rules, always been relations. What changes is how those rules express themselves. The universe we inhabit may be one expression among many. If so, then the vacuum is not the absence of reality. It is the lowest accessible expression of it within our emergent framework, a quiet hum beneath all existence, a baseline from which complexity arises. And this hum, this restless quiet, may be telling us something else. That information, not matter or energy, may be the true currency of the cosmos. The vacuum may store information. It may encode the rules that govern how space-time and particles appear. Its fluctuations may be the visible signatures of deeper informational processes. Once you begin to think this way, the line between physics and computation begins to blur. The vacuum becomes less like empty space and more like memory, a set of registers holding the rules of the game. Space and time become outputs, rendered from those rules when conditions allow. This is not to say that the universe is literally a computer in the human sense, but the analogy is powerful. In a computer simulation, the screen appears empty when nothing is being displayed. But beneath that blank screen, the hardware is active. Transistors switch, currents flow, information persists. The emptiness is an illusion created by the interface. Perhaps space-time is our interface, and the vacuum is the idle state of the display. Beneath it, the deeper system continues to operate, indifferent to our perception of emptiness. If that is the case, then the vacuum is not the end of explanation. It is the beginning of a deeper inquiry. What is this underlying system? What are its degrees of freedom? What rules govern it? And how does information flow within it? If not through space and time as we understand them, these questions may feel abstract, even speculative, but they are grounded in very real problems. The incompatibility of quantum mechanics and gravity, the mystery of vacuum energy, the emergence of space-time, all point toward the same unsettling conclusion. We are missing a layer. And as we stand at the edge of this realization, another phenomenon begins to glow with new significance. Black holes, objects where space-time and the vacuum are pushed to their limits, where information seems to disappear, only to re-emerge in subtle ways, where entropy, geometry, and quantum effects collide. Perhaps black holes are not just cosmic curiosities, but laboratories, places where the deeper structure of reality briefly reveals itself, forcing us to confront the possibility that information, not space or time, is the most fundamental thing of all. And so we step closer to the most extreme objects the universe can offer us, objects that seem almost designed to force our theories into confession. Black holes. For a long time, they were treated as mathematical curiosities, strange solutions to Einstein's equations that surely nature would avoid. But nature, it turns out, is far bolder than we are. Black holes exist. They form from collapsing stars. They merge. They ring like bells in space-time. And in their presence, our assumptions about space and time do not merely bend. They unravel. A black hole begins its life in a way that feels almost familiar. A massive star exhausts its nuclear fuel. Pressure drops. Gravity wins. The core collapses inward, faster and faster, until nothing we know can stop it. From the outside, we see a horizon form, an invisible boundary beyond which light can no longer escape. The event horizon. Cross it, and no signal you send will ever reach the rest of the universe. Not because of some magical barrier, but because space-time itself is tilted so severely that all future paths point inward. From far away, a black hole appears almost tranquil. It has mass. It may spin. It may carry electric charge. That is all. No hair, as physicists like to say. All the messy details of the collapsing star are erased, hidden behind the horizon. This simplicity is striking, and it hints at something deeper. Nature is compressing complexity into minimal description. But if you imagine falling into a black hole, the story becomes stranger. As you approach the horizon, time behaves oddly. To a distant observer, you appear to slow down. Your clock ticking ever more slowly, your image fading and reddening. You never quite cross the horizon in their time. You freeze. From your own perspective, however, nothing special happens at the horizon. You pass through without noticing. The laws of physics locally still apply. And yet, something profound has changed. Inside the black hole, the roles of space and time swap. The inward direction becomes as inevitable as the passage of time outside. You cannot stop moving toward the center any more than you can stop moving into the future. What we normally think of as space becomes time-like. What we think of as time becomes space-like. This is not metaphor. It is geometry. This inversion should already make us uneasy. We rely on time to order events. We rely on space to separate them. Inside a black hole, these categories lose their familiar meaning. The singularity at the center is not just a point in space. It is a moment in time, a future that cannot be avoided. The singularity itself is often described as a place where density becomes infinite and space-time curvature diverges. But as with the Big Bang, this infinity is almost certainly not a physical reality. It is a sign that our description has failed. Something has gone wrong with the assumption that space-time remains smooth and continuous all the way down. Perhaps the singularity is not a point of absurdity, but a point of transition, a phase change, a boundary between one regime of physics and another. Just as water turns into ice, perhaps space-time turns into something else entirely under such extreme conditions. And this is where black holes begin to whisper their deepest secrets. In the 1970s, something extraordinary was discovered. Black holes are not completely black. When quantum effects are taken into account near the horizon, black holes emit radiation. They have a temperature. They slowly lose mass. Given enough time, they evaporate. This was shocking. A black hole, which in classical general relativity is just a region of space-time, behaves like a thermodynamic object. Temperature implies microscopic degrees of freedom. Entropy implies counting. A black hole has entropy proportional to the area of its horizon, not its volume. This is deeply strange. It suggests that the information content of a region is encoded on its boundary. And here we encounter the information paradox. If a black hole evaporates completely, what happens to the information about the matter that fell in? Quantum mechanics insists that information is never destroyed. General relativity seems to say that anything crossing the horizon is lost forever. These two statements cannot both be true, at least not in their simplest forms. For decades, this paradox has resisted resolution, and that resistance is telling. It suggests that something fundamental is missing from our understanding. Black holes are not destroying information, nor are they trivial objects. They are doing something subtler. They are processing information. The modern view, emerging slowly and with much debate, is that black holes act as extreme information compressors. They take complex configurations of matter and encode them in the geometry and quantum state of the horizon. The information is not lost. It is scrambled, spread out, rendered inaccessible in any simple way. But in principle, it remains. This idea is radical, but it aligns with many hints we have encountered already. Space-time may be emergent. Geometry may encode information. The vacuum may be a structured ground state. Black holes, then, are places where this encoding becomes unavoidable, where geometry and information are forced into the same story. If information is preserved, then the interior of a black hole cannot be a dead end. It cannot simply annihilate the past. Something must exist behind the horizon that is consistent with quantum rules, even if it looks nothing like space and time as we know them. Some ideas suggest that the interior of a black hole is not a place at all, but a different regime of description. The horizon may mark the boundary between two effective theories. Outside, space-time and quantum fields behave in familiar ways. Inside, the degrees of freedom reorganize. New rules apply. This is unsettling, because it challenges the idea that space-time is a single, global structure. It suggests that space-time may be stitched together from regions governed by different effective laws. The event horizon is not merely a boundary in space. It is a boundary in description. And, this idea fits beautifully with what we have already suspected. That space-time is not fundamental, that it is a phase of a deeper system. Black holes may be places where that phase breaks down, where the underlying structure becomes dominant. From this perspective, a black hole is not a hole at all. It is a region where space-time gives way to something else, something more basic, something that does not admit a simple geometric interpretation. This reframes the fear we often associate with black holes. They are not cosmic shredders, destroying matter and meaning. They are transformers, converters. They take matter, energy, and information and translate them into a different language. Even the notion of falling into a black hole may be misleading. From the outside, we imagine an object crossing the horizon and disappearing. From the inside, there may be no sense of crossing at all. The horizon may be a feature of the external description, not a physical wall encountered by the infalling matter. Some approaches even suggest that the interior of a black hole may be equivalent to something else entirely. A region of space-time elsewhere, a different universe, or perhaps more conservatively, a different representation of the same underlying information. If space-time is emergent, then horizons are not absolute. They are context-dependent. What looks like an end from one perspective may be a beginning from another. The singularity, then, may not be a terminal point, but a gateway. This idea echoes what we suspected about the Big Bang, that it may not be a beginning, but a transition. Black holes and the origin of the universe begin to look less like opposite extremes and more like reflections of the same underlying phenomenon. Places where space-time is pushed beyond its domain of validity. And here, quietly, information takes center stage. The laws governing black holes seem to care deeply about information. Entropy scales with area. Horizons encode data. Evaporation releases scrambled messages. It is as if the universe is telling us that information, not geometry, is the true invariant. Matter falls into a black hole and loses its identity. Particles dissolve. Fields blend. What remains is information, stripped of form, compressed to its essentials. If that information persists, then it must persist in something more fundamental than space and time. This pushes us toward a remarkable conclusion. Black holes are not just astrophysical objects, they are probes. They reveal the limits of our concepts. They show us where space-time fails and information remains. If we listen carefully, black holes seem to be telling us that reality is not built from particles moving through space over time. It is built from relationships, from correlations, from information that can be encoded, transformed, and preserved even when space and time themselves become ambiguous. And once that realization settles in, another question arises, almost unavoidably. If information is what survives the collapse of space-time, if it is what black holes conserve and encode, then perhaps information is not just something that exists within the universe. Perhaps it is what the universe is made of. This is a quiet but profound shift. Matter becomes a pattern of information. Energy becomes a way information changes. Space becomes a way information is arranged. Time becomes a way information is updated. And if that is so, then the next step is clear. We must stop asking what things are made of and start asking what information is, how it flows, and how it gives rise to the world we experience. Because once we follow that thread, we may find that the deepest layer of reality is not space, not time, not matter, but something even more abstract and more fundamental still, waiting patiently beneath everything we have so far described. And so the idea returns, heavier now, more difficult to set aside. Information. Not as a metaphor, not as a poetic flourish, but as a serious candidate for the most fundamental ingredient of reality. After black holes, after horizons, after the quiet insistence that nothing is ever truly lost, it becomes hard to argue that matter sits at the base of existence. Matter dissolves, particles decay, fields fluctuate, even space-time itself seems willing to tear, stretch, and vanish under pressure, but information stubbornly remains. At first, this feels almost disappointing. We want reality to be built from something tangible, something we could imagine holding, or at least picturing. Information sounds abstract, mathematical, bloodless. But that reaction, I suppose, reveals more about our habits of thought than about the universe itself. We evolved to grasp objects, not patterns. We learned to survive by tracking shapes and motions, not correlations and constraints. Yet nature has never promised to conform to our instincts. In physics, information is not about meaning or interpretation. It is about distinction, about the fact that the universe can be in one state rather than another, a yes rather than a no, a spin up rather than spin down. A configuration that can, even in principle, be told apart from another. Information is difference that persists. When you describe a particle, what are you really doing? You specify its mass, its charge, its spin. You specify where it is relative to something else, how fast it is moving relative to something else. These are not substances. They are relational facts. They are bits of information about how one part of the universe relates to another. Quantum mechanics makes this explicit in a way classical physics never quite did. The wave function does not tell you what is. It tells you what could be observed with what probabilities. It encodes information about potential outcomes, not concrete realities. Before measurement, there is no fact of the matter about many properties. There is only a structured set of possibilities. And entanglement pushes this even further. Two particles, once entangled, cannot be fully described independently, no matter how far apart they travel. Their joint state contains information that does not belong to either particle alone. The information lives in the relationship, not here, not there, but between. This is deeply unsettling if you believe space is fundamental. How can something exist without a location? But it is far less troubling if space itself is emergent. If space is a way of organizing relations, not the container that relations sit within. In that case, information existing outside of space is not mysterious at all. It is expected. Black holes, again, are the loudest voices in this conversation. When matter falls into a black hole, all of its familiar properties vanish from the external description. Shape, composition, internal structure. Gone. What remains is mass, charge, and spin. And yet the entropy of the black hole tells us that vast amounts of information are still present, encoded somehow in the horizon. This encoding is not spatial in the usual sense. The information is not stored inside the black hole like objects in a box. It is smeared across the horizon in a way that defies our ordinary intuitions about storage and location. The black hole does not forget, it compresses. This compression suggests that information is more basic than the things it describes. Matter becomes a particular way of arranging information. Energy becomes a measure of how rapidly information changes. Geometry becomes a way of quantifying informational relationships. Once you begin to see the universe this way, many puzzles soften, not because they are solved, but because they are reframed. The information paradox ceases to be a paradox if information is the primary entity and space-time is secondary. Of course, information is preserved. Space-time is not allowed to destroy the thing that gives rise to it. Entropy, too, takes on a clearer role. It is not disorder in the everyday sense. It is missing information. When entropy increases, it is not that the universe becomes messier. It is that correlations become harder to track. Information becomes more diffuse, more scrambled, less accessible to local observers. The arrow of time itself may be rooted here. We remember the past, not the future, because information about the past is stored in records, in correlations that persist. Information about the future has not yet been encoded in the same way. Time's direction may be an emergent feature of how information accumulates and degrades, not a fundamental flow built into the universe. This idea becomes even more compelling when we consider that information does not obviously require time to exist. A pattern can exist timelessly. A mathematical structure does not age. It simply is. If the deepest layer of reality is informational, then time may be a derived concept, arising only when information is accessed or processed in a particular way. Some physicists have explored models in which the universe, at its most fundamental level, is static. All possible states exist in a timeless structure. What we experience as time is a sequence of informational updates as an observer moves through that structure. The universe does not evolve. We do. This is not to deny change, but to relocate it. Change is not something the universe does. It is something observers experience as they traverse correlations within the informational whole. Time is not a river. It is a map. And, this is where the idea starts to feel almost philosophical, even unsettlingly close to questions about consciousness. Because observers are not passive. To observe is to register information, to store it, to compare it. The very act of observation is an informational process. Quantum measurement, in this light, is not mysterious collapse. It is information becoming definite relative to an observer. The wave function does not physically collapse. It updates. A set of possibilities is reduced because information has been acquired. This does not mean consciousness causes reality in any mystical sense. But it does mean that observers are part of the informational story. They are not external witnesses. They are subsystems within the informational network, updating their internal states based on correlations with the rest. If information is fundamental, then the laws of physics are not laws about objects moving in space and time. They are laws about how information can be structured and transformed. They are constraints on correlations, rules that govern what patterns are stable, what transitions are allowed, what configurations are forbidden. The speed of light, then, may be understood as a limit on information transfer. Not because space imposes it, but because the underlying informational architecture does. Causality becomes a statement about consistency. Effects cannot precede causes because that would violate the coherence of the informational network. From this perspective, forces become secondary. They are effective descriptions of how information rearranges itself under certain conditions. Gravity, for example, may not be a force or even geometry, but an entropic effect, a tendency for information to organize itself in ways that maximize entropy subject to constraints. This idea has been explored in various forms, suggesting that gravity emerges from information-theoretic principles, that space-time geometry arises from patterns of entanglement, that distance itself measures how strongly subsystems are correlated. Near things are strongly entangled, far things are weakly entangled. Space becomes a map of informational closeness. If this is true, then the universe is not made of stuff. It is made of relationships. And relationships are informational by nature. This also sheds light on why mathematics describes the universe so well. Mathematics is the language of structure and relation. If reality is fundamentally informational, then mathematical descriptions are not approximations. They are glimpses of the underlying order. The effectiveness of mathematics stops being mysterious. We are not discovering equations that coincidentally match reality. We are uncovering the rules by which information organizes itself. This brings us back, gently, to the idea of the universe as a kind of computation. Not a literal computer, with hardware and code, but a process governed by informational rules. The universe updates, patterns evolve, correlations shift. Space and time emerge as ways of organizing those updates. In such a picture, asking where information flows becomes tricky. Information does not flow through time the way water flows through a pipe. Information simply exists in different configurations. What we call flow is the change in those configurations relative to an observer. So when we ask where information goes inside a black hole, or where vacuum fluctuations reside, we may be asking the wrong kind of question. Information does not need a place. Place is something that information creates when it is rendered spatially. And this has a profound consequence. It suggests that there may be many ways to render the same underlying informational structure. Space-time as we know it may be only one of them, a particular interface, a particular projection. If information is fundamental, then different emergent realities could arise from different organizational principles applied to the same informational substrate, different rule sets, different effective laws, different experiences of space and time. This is where the idea of multiple universes takes on a new meaning, not as bubbles floating in a larger space, separated by vast distances, but as alternative renderings of information, orthogonal to one another, not spatially, but structurally. Our universe may be one way information organizes itself into a coherent, stable pattern with observers like us embedded within it. Other organizations may exist, inaccessible not because they are far away, but because they are governed by different relational rules. This is an unsettling thought, but also a liberating one. It suggests that reality is far richer than the thin slice we experience, that what we call the universe is not the whole story, but one chapter in a much larger book written in the language of information. And yet, even as this picture begins to cohere, it raises new questions. If information is fundamental, what determines its rules? Why these correlations and not others? Why does information organize itself into stable structures at all? We have replaced matter with information, but we have not reached the bottom. We have uncovered a deeper layer, but beneath it there may be something even more abstract. Rules that govern information itself, meta-laws, constraints on constraints. And once you begin to think this way, the notion of a single universe begins to dissolve. What we call reality may be one expression of a deeper informational architecture that supports many possible expressions, not separated by distance or time, but by logic. This naturally draws us toward the next idea. If information is the substrate, then different universes may correspond to different rule sets operating on that substrate, different ways of rendering the same underlying informational potential, a multiverse, not of space, but of structure. And so, without closing the door, without pretending to have reached the final answer, we find ourselves standing before another threshold. The possibility that reality is layered, that beyond our universe lies not emptiness, but alternative ways information can give rise to worlds. And once that possibility is admitted, the question is no longer, where are the other universes? But how many ways can information choose to become real? And so, the idea of information as the deepest layer begins to open a door that many find unsettling. If information is fundamental, if space-time is a way that information organizes itself into something we can inhabit, then the universe we experience may not be the only possible rendering, not the only way reality can be arranged. And this is where the word multiverse quietly changes its meaning. When most people hear multiverse, they imagine bubbles drifting in a vast cosmic ocean, universes scattered through a larger space, separated by unimaginable distances. But that picture, comforting as it may be, is still trapped inside spatial thinking. It assumes that space is the container for everything else, and we have already begun to let go of that assumption. If space itself is emergent, then other universes do not need to be elsewhere in space. They do not need to be far away. Distance may be the wrong concept entirely. Instead, they may be layered differently, stacked not by location, but by rules. Think for a moment about a computer screen. At any instant, it shows a single image, but beneath that image, there may be many layers, background processes, hidden windows, entire virtual environments running silently. They are not far away. They are orthogonal to what you see. Accessing them requires not travel, but a change of rules, a different interface. Perhaps reality is structured in a similar way. The universe we experience may be one rendering of an underlying informational architecture, one stable solution among many. Other solutions may exist simultaneously, not separated by space or time, but by their rule sets. Different ways information can arrange itself into coherent worlds. In this picture, the multiverse is not a collection of places. It is a collection of possibilities. A space not of distance, but of structure. Each universe corresponds to a particular configuration of laws, constants, and relationships. And our universe is simply the one we find ourselves inside, because it is the one compatible with observers like us. This idea often appears in discussions of cosmology and particle physics, especially when trying to explain why the constants of nature have the values they do. Why is gravity so weak? Why do particles have the masses they have? Why does chemistry work at all? In a single universe framework, these questions feel almost metaphysical. In a multiverse of rule sets, they become statistical. We observe these values because only these values allow observers to exist. But the deeper shift is not about explaining constants. It is about rethinking what a universe is. A universe may not be a region of space. It may be a self-consistent informational structure, a stable pattern in the space of all possible patterns. If information is fundamental, then there is no reason to expect only one way of organizing it. Just as there are countless possible games that can be defined by different rules, there may be countless possible realities, each internally consistent, each obeying its own logic. Some may resemble ours, many may not. And, this is where intuition begins to fail completely. We are accustomed to thinking that reality must be singular, one world, one timeline, one set of laws. But this expectation may be nothing more than a psychological bias, born from the fact that we can only experience one configuration at a time. Even within our own universe, we already accept that different effective laws operate at different scales. Quantum rules at small scales, classical rules at large scales, thermodynamic rules for large systems. None of these invalidate the others. They are layers of description. Perhaps the multiverse is simply an extension of this idea to the largest possible scale. Different universes may correspond to different effective descriptions emerging from the same underlying informational substrate. The substrate itself does not choose one universe. It allows many. Which one is experienced depends on how information is organized locally. This also explains why other universes may be forever inaccessible. Not because they are too far away, but because there is no shared interface, no common language, no overlap in the way information is rendered. Communication requires shared structure. Without it, there is nothing to transmit through. From this perspective, the idea of traveling to another universe becomes meaningless. Travel assumes space. It assumes continuity. It assumes a path. But if universes differ in their underlying rule sets, there may be no path connecting them, only a difference in organization. This reframes the role of dimensions as well. When physicists speak of extra dimensions, we often imagine them as additional directions in space, curled up or hidden, but perhaps dimensions are not spatial at all. Perhaps they are degrees of freedom in the underlying informational structure. Different ways rules can be applied, different axes in the space of possible laws. In that sense, our familiar three-dimensional space may be just one layer, a projection, a user interface optimized for certain kinds of stable structures. Other layers may exist, overlapping not in space, but in the rule space. They are not containers within our universe. They are alternative ways of organizing the same deeper reality. This idea also sheds light on why the universe feels finely balanced. Small changes in fundamental constants would render stars unstable, chemistry impossible, complexity unattainable. In a single universe picture, this feels miraculous or troubling. In a multiverse of rule sets, it is expected. Most configurations do not produce rich structures. A few do. We find ourselves in one of those few because otherwise there would be no one to ask the question. But notice something subtle here. This explanation does not require that all universes exist in space or time. It only requires that all configurations are allowed in the informational substrate. Existence becomes logical consistency rather than physical location. This is deeply counterintuitive. We are used to equating existence with being somewhere. But information does not need a where. A mathematical structure exists whether or not it is instantiated in space. A rule exists whether or not it is applied. Perhaps universes exist in this sense, as allowable patterns in the deep architecture of reality. And if that is the case, then the multiverse is not something that came into being. It did not start. It did not expand. It simply is, a timeless set of possibilities. What changes is which possibility is rendered, which one is experienced. This brings us back to the idea of rendering. Our universe may be the result of a particular rendering pipeline, a way information is processed into spacetime, matter, energy, and causality. Other renderings may process information differently, producing realities with no space or no time or no stable particles. In some universes, there may be no observers at all. In others, observers may exist, but experience reality in ways utterly alien to us. The multiverse, in this sense, is not a collection of worlds like ours. It is a vast landscape of potential structures, most of which do not resemble anything we could recognize. This perspective also dissolves a common objection. People often ask how we could ever test the existence of other universes. But if universes differ by rule sets rather than location, then direct testing may be impossible in principle. This does not automatically make the idea unscientific. It means that the multiverse may function as an explanatory framework rather than a directly observable entity. Science has always used unobservable entities to explain observable patterns. Fields were once unobservable. Atoms were once unobservable. Even spacetime curvature was once a mathematical abstraction. What matters is not observability in isolation, but explanatory power and coherence. The multiverse of rule sets offers a coherent way to understand fine-tuning, emergence, and the apparent contingency of physical laws. It aligns naturally with the idea that information is fundamental and spacetime is emergent. It does not require new particles or forces. It requires a shift in perspective. And, this shift can feel unsettling because it undermines the specialness of our universe. But it also places us within a much grander context. Our universe becomes one story among many, one expression of a deeper narrative written in information. Yet this picture is still incomplete, because even if many universes exist as different informational renderings, they may not be entirely independent. They may share a common substrate, a common logic, a deeper layer that defines what kinds of rule sets are possible in the first place. This raises another question. If universes differ by rules, then what determines the rules? Are all logically consistent rule sets allowed? Or is there a deeper selection principle, a metastructure that constrains what kinds of realities can exist at all? At this point, the multiverse stops being the end of explanation and becomes another clue, a sign that reality may be layered not just once, but many times. Information at the base, rule sets above it, emergent universes above that, observers embedded within. And as we stand here, contemplating a reality not of places, but of possibilities, another assumption quietly begins to wobble. The assumption that cause must always precede effect, that events must be ordered in a simple, linear way. Because if universes are different renderings of information, then causality itself may be part of the interface, not the foundation. Perhaps cause and effect are not fundamental features of the informational substrate. Perhaps they are rules that apply only within certain renderings. And if so, then the network of reality may be far less linear, far more interconnected than our everyday experience suggests. This thought draws us naturally toward the next question. If causality is emergent, if it is a rule rather than a necessity, then what happens when that rule is relaxed or reinterpreted? What does reality look like when cause and effect are no longer chained in a simple line, but woven into a deeper, more complex web? And that is where our curiosity, inevitably, begins to drift next. And so we arrive at a rule so deeply woven into our thinking that we rarely notice it at all. Cause before effect, past giving birth to future. One event pushing another along a line we call time. Causality feels not just physical, but moral, psychological, inevitable. We plan because causes produce effects. We regret because effects trace back to causes. Our entire sense of responsibility, prediction, and understanding is built upon this quiet assumption that the universe itself respects a strict order. But once we have loosened our grip on space, once time itself has begun to look emergent, once information replaces matter as the deepest currency, causality begins to tremble. Not collapse outright, but reveal its seams. And, that is an uncomfortable moment, because causality feels like the last thing we can afford to lose. In classical physics, causality is clean. Forces act locally. Signals propagate through space over time. If something happens here, its influence spreads outward, never faster than a well-defined speed. Effects never precede causes. The universe behaves like a well-ordered chain of dominoes. This picture is intuitive, stable, and deeply reassuring. Relativity preserves this structure but reshapes it. Cause and effect are no longer absolute. They depend on the observer. Events that are simultaneous for one observer may not be for another. Time stretches and contracts. Yet, causality itself remains protected. The light cone draws a boundary around what can influence what. No signal can jump outside it. The order of cause and effect is preserved within that structure. Quantum mechanics, however, complicates this picture in subtle ways. Entangled particles share correlations that do not respect spatial separation. Measurement outcomes appear linked instantaneously, regardless of distance. This does not allow information to be sent faster than light, but it does force us to reconsider what we mean by influence. The correlations exist without any signal traveling between the particles at the moment of measurement. At first, this seems like a technical curiosity, a quirk of probability, but the deeper implication is unsettling. The universe appears to coordinate outcomes without a clear causal mechanism operating in spacetime. Something deeper is enforcing consistency. This is where causality begins to look less like a fundamental law and more like an emergent constraint, a rule that holds within certain renderings of reality, but not necessarily in the underlying informational substrate. If information is fundamental, then the universe may not evolve by causes pushing effects forward. It may instead be governed by global consistency conditions. Patterns must fit together. Correlations must agree. What we perceive as cause and effect may be the way these consistency requirements appear when experienced sequentially by observers embedded in time. Imagine reading a novel. The events on page 50 do not cause the events on page 100. They are all part of a single structure. Yet as a reader, you experience them sequentially. Earlier pages explain later ones. Later revelations reshape your understanding of earlier scenes. From within the story, causality exists. From outside, it is simply structure. Perhaps the universe is more like a finished novel than a story being written line by line. The entire informational structure exists timelessly. What we call causation is the way that structure is revealed to observers moving through it. This idea gains traction when we consider that many fundamental equations of physics are time-symmetric. They work just as well forwards as backwards. The laws themselves do not distinguish past from future. The arrow of time arises from boundary conditions, from entropy, from how information is distributed and recorded. Causality may arise in the same way. In this view, causes do not produce effects in an absolute sense. Instead, events are arranged in patterns that are self-consistent. An effect may appear to follow a cause, because that ordering is part of a stable informational configuration. But nothing prevents, at the deepest level, correlations that look like influence running backward in time. Indeed, quantum theory allows such interpretations. In some formulations, future measurements help define the present state, not by sending signals backward in time, but by constraining the overall structure. The present is not determined solely by the past. It is determined by the requirement that the entire pattern be consistent. This is deeply counterintuitive. We are used to thinking that the past fixes the future, not the other way around. But if time is emergent, then the distinction between past and future may be perspectival rather than absolute. Consider again black holes. Information about infalling matter seems to be smeared across the horizon and later released during evaporation. From one perspective, the information goes in, then comes out. From another, it was never really inside in the first place. The ordering of events depends on the description. Causality becomes slippery. Or consider the multiverse of rule sets we have been exploring. If different renderings of reality exist, each with its own effective laws, then causality may be one such law. A flag in the rendering engine, enabled here, disabled or modified elsewhere. Within our universe, causality appears strict because it is necessary for stable observers like us. Predictability requires it. Memory depends on it. Life itself relies on reliable cause and effect relationships. But that does not mean causality is built into the foundation of reality. It may simply be a rule that applies in this layer. This perspective also helps resolve apparent paradoxes. Reverse causality, for example, is often dismissed as nonsense. Effects before causes, signals from the future. But in an informational framework, reverse causality is not forbidden. It is merely constrained. Information does not flow backward in time in our universe because that would break consistency with how our rendering handles updates. But at the deeper level, information may not flow at all. It may simply exist in correlations that do not respect temporal ordering. This is why attempts to send messages to the past always fail, despite quantum weirdness. The underlying informational structure enforces consistency. You cannot create paradoxes not because time travel is impossible in principle, but because inconsistent informational configurations are not allowed. This idea is sometimes called the consistency principle. The universe does not forbid strange correlations, it forbids contradictions. Whatever happens must fit into a single coherent pattern. From this angle, causality becomes less like a chain and more like a network. Events are not ordered by simple before and after relationships, but by constraints that ensure global coherence. Some constraints appear temporal, others appear spatial. All are manifestations of the same deeper rule. And, this network view of causality aligns beautifully with the informational picture we have been building. Information does not propagate like a wave through time. It constrains the entire structure. Local updates must agree with global rules. This also reframes free will in an interesting way. If causality is emergent, then the future may not be fully determined by the past, but neither is it arbitrary. Choices may be part of the informational structure, not violations of it. Freedom may arise from underdetermination rather than from breaking laws. In such a universe, prediction becomes limited not because reality is random, but because information is distributed. No observer has access to the full structure. We see only a slice. From within that slice, the future appears open. This perspective also explains why causal paradoxes feel threatening. They challenge not physics, but our narrative instincts. We tell stories with beginnings, middles, and ends. We assign responsibility. We look for origins. But the universe may not be obligated to respect narrative order at its deepest level. If causality is a rule of the rendering rather than the substrate, then it may break down in extreme conditions, near black holes, near the origin of spacetime, at the boundaries between universes. In those regimes, cause and effect may blur into mutual constraint. This is not to say that anything goes. The universe is not chaotic at the fundamental level. It is deeply structured. But that structure may not privilege time in the way we do. Once we accept this, the idea of a single timeline begins to look like another convenience, a useful approximation that works within our experience, but not necessarily beyond it. Reality may be better described as a web of correlations, with time emerging as one way of traversing that web. And this naturally brings us to another deeply unsettling idea, the role of the observer. Because causality is not just about events, it is about perspective, about how information is accessed and updated. An observer embedded in spacetime experiences causality because their own informational processing depends on memory. Records of the past exist. Records of the future do not. This asymmetry shapes experience. It may also shape physics as we perceive it. But what if the observer is not merely inside the universe, but part of the rendering process itself? What if observation is not passive, but active? What if the act of observing is a fundamental part of how information becomes definite? Quantum mechanics already hints at this. Measurement changes the system. Observation updates the state. The observer cannot be cleanly separated from what is observed. If causality is emergent, then the observer may be one of the mechanisms through which causal structure arises. Conscious systems process information sequentially. They create internal timelines. They impose order on correlations. This suggests that causality may be as much about how observers exist as about how the universe exists. The arrow of cause and effect may be tied to the arrow of experience. And once that possibility is on the table, another question quietly emerges. If observers play a role in how reality is rendered, then what exactly is an observer? Not a human necessarily, but any system capable of registering, storing, and updating information. Where does observation happen? Does it happen inside space-time, or does it straddle the boundary between the informational substrate and the rendered universe? That question pulls us gently, but inexorably, toward the next layer of the story. Because once causality itself begins to look like a rule rather than a necessity, once the flow of events becomes a perspective-dependent feature, the observer can no longer be treated as a spectator. They may be part of the machinery, part of the pipeline through which information becomes the world we experience. And so, without closing the door on causality, without dismissing it, we begin to see it for what it may be, not the foundation of reality, but one of its most successful illusions. A rule that works so well in our layer of existence that we forget it might not apply everywhere. And with that realization, our attention naturally turns to the one thing we have so far treated as separate from the universe itself, the observer. And so the circle tightens around a question we have carefully avoided for as long as possible. If causality is not fundamental, if time and space are emergent, if information sits beneath them all as the true currency of reality, then what about the observer, the one who measures, the one who experiences, the one for whom a universe appears at all? We often treat the observer as an afterthought, a passive witness standing inside the cosmos, pointing instruments outward. But quantum mechanics, quietly and relentlessly, refuses to let us do that. From the very beginning, quantum theory has carried an uncomfortable message. Observation is not neutral. Measurement does not merely reveal reality, it participates in it. The wave function evolves smoothly according to precise mathematical rules, until a measurement occurs. Then, suddenly, probabilities collapse into a definite outcome. We call this collapse, but we rarely ask the most troubling question of all. Collapse into what? Where does the wave function go when it collapses? It does not drift into space. It does not fall into time. It does not settle anywhere we can point to. Something else happens. Information is updated. A potential becomes an event, and that update is inseparable from the act of observation itself. For decades, physicists tried to push the observer out of the picture, to treat measurement as just another physical interaction. A detector clicks. A particle hits a screen. End of story. But this move never quite works. Because no matter how large you make the detector, no matter how classical you make the apparatus, you still have to explain why one outcome occurs rather than another. The mathematics gives probabilities, not facts. Facts appear only when information is registered. This is not about human consciousness in any mystical sense. An observer need not be a person. It can be any system capable of storing information in a stable way. A photographic plate, a memory register, a neuron. What matters is not awareness, but record-keeping. Observation is the act of creating a record. And, this is where the story becomes quietly radical. Because records do not exist in isolation. They exist within a larger informational structure. An observer is not outside the universe looking in. The observer is a subsystem within the universe, processing information according to the same underlying rules. If information is fundamental, then observers are not accidental. They are natural consequences of how information organizes itself. Systems that can store and update information arise because they are stable patterns within the informational substrate. Observers are not add-ons, they are features. This reframes the measurement problem completely. The collapse of the wave function is not a mysterious physical jump. It is an update in the informational state of the observer relative to the rest of the system. The universe does not choose an outcome in an absolute sense. An outcome becomes definite relative to an observer. In this view, reality is not a single global state that everyone shares. It is a web of relative states, each defined by informational relationships. Different observers may assign different wave functions to the same system, and none of them are wrong. They are simply describing reality from different informational perspectives. This idea is unsettling because it undermines the notion of an objective, observer-independent reality. But perhaps that notion was always an approximation, useful, powerful, but incomplete. At the deepest level, reality may be relational all the way down. If spacetime is emergent, then observers are not embedded in spacetime in the way we usually imagine. They are embedded in the informational substrate that gives rise to spacetime. Space and time are part of the rendering. Observers are part of the rendering pipeline. Think again of a simulation, not as a claim about our universe being artificial, but as an analogy. In a simulation, characters experience a world with space, time, and causality. But the processes that generate that world exist at a deeper level. The characters do not live inside the hardware. They live inside the output. Yet their actions influence how the output evolves. In the same way, observers may not stand inside the universe as passive occupants. They may be active participants in how the universe is rendered, not because their thoughts shape reality, but because information updates are an essential part of how reality appears at all. This idea helps explain why the observer seems to play such a central role in quantum mechanics, but such a minor role in classical physics. At large scales, information is abundant. Records are everywhere, outcomes are stable. The universe appears objective. At small scales, information is scarce. Correlations dominate. Observation matters. The classical world emerges because many observers agree, not because reality is independent of observation, but because information is redundantly recorded. A table looks solid because countless degrees of freedom encode its existence. Photons bounce, atoms vibrate, records proliferate. The world becomes robust. But at the quantum level, information is fragile. A single interaction can change the entire description. There is no redundancy. Observation becomes decisive. This also reframes the role of consciousness in a careful but profound way. Consciousness is not required for physics to work, but conscious observers are exceptionally efficient information processors. They integrate information over time. They form memories. They create narratives. And narratives impose causal order. An observer experiences a sequence of events because their internal state updates sequentially. Memory creates a past. Anticipation creates a future. The flow of time may be inseparable from the way observers process information. In this sense, time does not flow universally. It flows for observers. It is an emergent feature of information processing. Without observers, the universe may still exist as an informational structure, but without a narrative thread. This idea can feel disturbing, as if it places too much weight on observation. But it does not elevate observers to cosmic creators. It places them where they belong, inside the system, subject to its rules, necessary for certain features to appear, but not sovereign over reality. The observer does not create the universe. The observer creates experience. And this distinction matters. The informational substrate exists whether or not observers arise. But certain aspects of reality only become meaningful in the presence of observers. Measurement, probability, causality, time. These may be observer-dependent phenomena. This also helps explain why physics struggles when it tries to describe the universe as a whole. Cosmology has no external observer. There is no outside vantage point from which to measure the universe. And yet our theories assume one. We write down wave functions for the entire cosmos. We talk about its quantum state. But who observes it? Perhaps the question is ill-posed. Perhaps the universe does not have a single quantum state in the way a particle does. Perhaps it is a collection of relative states, defined by the informational relationships between its subsystems. If that is true, then the universe does not collapse its wave function. Observers within it update theirs. This perspective also dissolves some of the anxiety around determinism and free will. If the future is not fixed globally, but becomes definite only relative to observers as information is updated, then the future is genuinely open from within. Not because laws are broken, but because information is incomplete. Choice becomes meaningful because observers are not omniscient. They operate with partial information. Their actions influence future correlations, not by violating physical laws, but by participating in the update process. This is not a loophole. It is a feature. And, once you begin to see observers this way, the universe starts to look less like a machine grinding forward and more like a conversation. information exchanged, records created, perspectives formed. Reality unfolding not as a single story but as many interwoven ones. This does not lead to solipsism. Other observers exist. Other perspectives matter. The informational substrate enforces consistency between them. You cannot observe a reality that contradicts everyone else's records. But it does mean that objectivity is collective, not absolute. Objectivity emerges when many observers agree. Agreement is not guaranteed. It is achieved. This idea also casts new light on the role of life. Life is not just chemistry in motion. It is organized information processing. Living systems persist by maintaining internal states, far from equilibrium. They store information about their environment. They act on that information. Life is not an accident layered on top of physics. It is one of the ways physics expresses itself when information becomes complex. Consciousness, in this light, may be an extreme form of information integration, a system that not only stores information, but models itself as an observer within the system. A feedback loop, a mirror turned inward. This does not solve the hard problem of consciousness, but it places it within the same framework as everything else. Consciousness is not outside physics. It is a particular informational process arising within it. And if observers are part of the rendering pipeline, then the universe we experience is not a neutral snapshot. It is a negotiated outcome, a result of interactions between informational structures. Reality is not delivered to observers. It is co-constructed by them. This does not mean reality is subjective in the everyday sense. It means it is relational. It exists in the space between observer and observed. And now, having followed this thread as far as it will take us, another question begins to glow faintly in the background. If observers are part of the rendering process, if reality appears through information updates relative to them, then what about the things we never observe? The vast, unseen components of the universe, the dark sector, the matter and energy that shape the cosmos without ever announcing themselves directly. Are they truly separate from observation? Or are they simply parts of the informational structure that never intersect with our rendering pipeline? This question draws us onward, because once the observer steps into the center of the story, the absence of observation becomes just as important as its presence. And in the shadows beyond our instruments, something vast and influential seems to be at work, shaping the universe while remaining stubbornly invisible. And so our attention turns, almost reluctantly, toward what we do not see, toward the vast components of the universe that shape everything we observe, yet never reveal themselves directly. Dark matter, dark energy, names that sound provisional, almost apologetic, as if we are admitting ignorance rather than naming understanding. And perhaps that is exactly what they are. Placeholders, shadows cast by something deeper that does not intersect with our senses, our instruments, or even our most trusted theories in the way ordinary matter does. For decades, astronomers mapped the cosmos assuming that what shines is what matters. Stars, galaxies, glowing gas clouds. Light was our guide, our messenger. We built telescopes to catch it, stretch it, decode it, and for a while this worked beautifully. But then cracks appeared. Galaxies were rotating too fast. Clusters were holding together when they should have flown apart. Light was bending around invisible masses. The universe was behaving as if there were far more substance present than we could see. The simplest explanation was that something unseen was there. Matter that does not emit or absorb light. Matter that interacts gravitationally but not electromagnetically. Dark matter. Not dark because it is black, but dark because it is silent to our instruments. And this idea, modest at first, grew unavoidable. Remove dark matter from our equations and the universe falls apart. Galaxies unravel, structures never form. The cosmic web dissolves. And yet, despite decades of searching, we have never detected a dark matter particle directly. We infer its presence entirely through its gravitational influence. It pulls, but it does not speak. It shapes, but it does not shine. It is everywhere, and nowhere we can touch. Then there is dark energy, even more mysterious. In the late 20th century, we discovered that the expansion of the universe is accelerating. Not slowing down under gravity as we expected, but speeding up. Something is pushing space apart. Not a force in space, but a property of space itself. Or so it seems. Dark energy behaves like a pressure inherent to the fabric of the universe. A uniform, persistent influence that grows more important as the universe expands. It does not clump. It does not dilute in the way matter does. It simply is. And it dominates the cosmic budget. Ordinary matter, everything we know and love, is a minor ingredient. Dark matter outweighs it several times over. Dark energy outweighs both by far. So here we are, you see, realizing that nearly all of the universe is invisible to us. Not hidden behind distance, but hidden behind incompatibility. It does not interact with us in the ways our senses and instruments are designed to detect. And that fact alone should make us pause. Because earlier, we began to suspect that observation itself is part of the rendering pipeline. That reality appears in certain forms because of how information is accessed. Perhaps the dark sector is not dark because it is absent. Perhaps it is dark because it belongs to a different layer of rules. If spacetime is emergent, if matter and energy are manifestations of information, then the distinction between visible and invisible may reflect not presence or absence, but coupling. Ordinary matter couples strongly to the electromagnetic interaction. That is why it forms atoms, emits light, builds complexity. Dark matter does not. It may couple only through gravity, or through something even more subtle. But what if gravity itself is not fundamental? What if it is an emergent information-theoretic effect, as some ideas suggest? In that case, dark matter may not be matter at all. It may be an artifact of how information organizes itself at large scales. A correction term. A shadow cast by degrees of freedom that live outside our space-time rendering. Consider this carefully. We observe gravitational effects that cannot be explained by visible matter. We assume unseen matter must be present, but that assumption rests on the idea that gravity is sourced only by matter in space. If gravity instead emerges from information density or entanglement structure, then what we interpret as extra mass may be something else entirely, a feature of the underlying informational architecture. Dark matter could be the gravitational signature of information that is not rendered as particles, information that does not participate in our layer of physics, but still influences the geometry that our layer emerges from. This would explain why dark matter behaves so differently from ordinary matter, why it does not form atoms, why it does not radiate, why it passes through everything as if it were not there. It may not be there in the way we think of there. It may exist in a different sector of the informational substrate. Dark energy pushes this idea even further. Its effects look less like matter and more like a property of space, or perhaps a property of the rules that generate space. A pressure that arises not from particles, but from the vacuum itself. But earlier, we questioned what the vacuum really is. Not empty space, but a ground state of something deeper. A sea of fluctuations, a baseline configuration. If dark energy is tied to the vacuum, then it may reflect properties of the underlying substrate rather than anything that lives within space-time. The accelerated expansion of the universe may not be driven by a mysterious substance filling space. It may be driven by how the rendering rules scale as the universe grows. A pressure not of space, but of the environment from which space emerges. Imagine again the idea of space-time as an interface, a user interface that presents reality in a certain way. As the system evolves, the interface may adjust. Scaling behaviors may change. What we perceive as dark energy could be the interface compensating for deeper informational constraints. This would also explain why dark energy has a remarkably small but non-zero value. It is not a fundamental constant in the usual sense. It is a parameter of the rendering, a result of how the deeper system projects into space-time. And This perspective helps dissolve a persistent frustration. We keep trying to detect dark matter particles. We keep trying to pin down dark energy as a field or a fluid. But what if we are looking in the wrong place? What if these phenomena are not inhabitants of space-time at all, but signatures of something that transcends it? This does not mean dark matter and dark energy are imaginary. On the contrary, their effects are real, measurable, undeniable. But their ontology may be different from what we assume. They may belong to a different category of existence. In an informational framework, the universe consists of many interacting sectors. Some sectors couple strongly to observers, others do not. The dark sector may be composed of degrees of freedom that rarely, if ever, intersect with our observational pipeline. They influence the global structure, but not the local details we are sensitive to. This idea aligns naturally with everything we have uncovered so far. Observers are part of the rendering. Causality is a rule, not a necessity. Space-time is emergent. Information is fundamental. Why should all information be rendered in the same way? The dark sector may simply be information that is not rendered as particles or fields in our layer. It exists, but not for us. It shapes the cosmos, but does not announce itself to our senses. This also reframes the cosmic coincidence problem. Why is dark energy becoming dominant now? Why does it matter at this stage of cosmic history? Perhaps because observers like us arise only during a narrow window, when the rendering produces stable structures. The dominance of dark energy may be part of the life cycle of a rendering, not a coincidence. In this view, universes may have phases. Early on, information organizes into dense structures. Matter dominates, stars form, observers arise. Later, the rendering shifts. Expansion accelerates. Structures thin out. Observation becomes increasingly difficult. Eventually, the universe may fade into a quiet, diffuse state, still rich in information, but poor in complexity. Dark energy may not be a destroyer of structure, but a transition marker, a signal that the rendering is entering a new regime. This perspective also explains why the dark sector has been so resistant to unification. We keep trying to shoehorn it into particle physics or classical fields, but it may belong to a different descriptive layer altogether. Trying to describe it using our familiar tools may be like trying to describe the operating system of a computer using the physics of pixels on the screen. The dark sector may live in the rule space rather than the space of objects. It may not be something that moves or interacts in time. It may be something that defines how time and interaction occur in the first place. And if that is true, then the dark sector is not a mystery to be solved by building bigger detectors alone. It is a clue pointing toward the architecture of reality itself. We often say that the universe is mostly dark, but perhaps a better way to say it is that the universe is mostly not rendered for us. Our experience is a narrow slice of a much richer informational landscape. This is humbling. It reminds us that what we perceive is not the totality of what exists, that reality does not owe us transparency, that our theories are interfaces, not mirrors. And yet there is something profoundly reassuring here as well. The universe is not hiding from us out of malice or indifference. It is simply larger than the slice we inhabit. Dark matter and dark energy are not enemies of understanding. They are invitations. They invite us to expand our models, to question our assumptions, to consider that existence itself may be layered, with different sectors obeying different rules, interacting only indirectly through shared structure. And this brings us gently to the final threshold. If space and time are interfaces, if information is the substrate, if observers are part of the rendering pipeline, and if much of reality exists in sectors beyond our direct perception, then the universe itself may not be the fundamental thing we thought it was. It may be an output, a display, a particular manifestation of a deeper system. And the next step, the final one, is to ask what that system looks like when we stop thinking in terms of universes and start thinking in terms of architecture. What kind of engine could generate space, time, matter, observers, and dark sectors alike? And what does it mean to look beyond space-time itself? not as a poetic gesture, but as a scientific necessity. And so we come gently to the edge of the map, not the edge of the universe, but the edge of how we have been thinking about it. For centuries, we believed the universe was the ultimate container. Space was the stage. Time was the river. Matter and energy were the actors moving upon it. Everything that existed inside the universe. And yet, step by step, that picture has quietly fallen apart. We began by questioning beginnings, realizing that the Big Bang may not be the birth of everything, but the earliest moment our current models can still describe. We loosened our grip on space, discovering that what we observe is only a signal-limited bubble, not the whole of what may exist. We saw space-time bend, stretch, and fail, hinting that it is not a substance, but a behavior. We watched quantum mechanics refuse to sit comfortably on the space-time stage, and we followed that discomfort into the vacuum, where emptiness revealed itself as a restless sea. We listened to black holes, those brutal teachers, telling us that information survives even when space and time do not. We elevated information from bookkeeping tool to foundational ingredient. We allowed universes to multiply, not across distance, but across rules. We watched causality soften into a network rather than a chain. And finally, we invited the observer inside the machinery, not as a master, but as a participant. Now, at this point, something becomes unavoidable. The universe itself may not be fundamental. It may be an output. This is a difficult thought to sit with. The universe feels ultimate, vast, all-encompassing. How could it be anything but fundamental? But feeling has never been a reliable guide to ontology. The earth felt flat. Time felt absolute. Space felt empty. Each time nature asked us to let go. If space-time is emergent, then it behaves less like an operating system and more like a user interface, a way complex underlying processes are presented in a form that is navigable, stable, and meaningful for embedded observers. A user interface hides complexity. It does not reveal the circuitry beneath. It shows icons, windows, flows, because those are useful. Perhaps space and time are like that. Not lies, but abstractions. They are real in the same way a desktop is real. You can move files, you can open folders, you can work. But the desktop is not where the computation happens. It is where the computation appears. If that is the case, then asking what exists beyond space-time is like asking what exists beyond the screen. The answer is not nothing. It is structure, rules, architecture. This reframes the meaning of beyond. Beyond space-time does not mean somewhere else. It means a deeper layer of description, a layer in which the concepts of distance and duration no longer apply, because they are products, not inputs. In this deeper layer, there may be no space to be in, and no time for things to happen in. There may only be relationships. Constraints. Information structures, update rules, and from those, under certain conditions, a space-time rendering emerges. This idea can feel uncomfortably close to metaphysics, but it is driven not by philosophical whim, but by physical necessity. Our best theories break when pushed too far, not because nature becomes irrational, but because our categories fail. When we try to describe the origin of the universe, space-time dissolves. When we try to describe black hole interiors, space-time collapses. When we try to unify gravity and quantum mechanics, space-time refuses to cooperate. Over and over again, space-time signals that it is not the bedrock. So what might the bedrock look like? One possibility is that reality is governed by a set of fundamental informational rules. Not laws in time, but constraints that define which informational structures are allowed. These rules do not evolve. They are not caused. They simply are. From them, different renderings can arise, including the space-time universe we experience. In such a picture, the universe is not a thing, but a process, or perhaps more precisely, a result of a process. It is what you get when the underlying rules are rendered in a particular way, under particular boundary conditions, producing stable structures like particles, fields, stars, observers. This helps explain why the laws of physics appear fine-tuned. They are not chosen, they are selected by stability. Only certain rule configurations produce long-lived, self-organizing structures capable of observation. Many configurations may exist at the deeper level, but most do not render worlds. This also explains why physics feels both rigid and contingent. Rigid within the universe, contingent when viewed from outside it. The rules inside the rendering are precise, but the existence of this particular rendering may not be necessary. And, that can feel unsettling. We like to believe that the universe had to exist, that it is inevitable. But inevitability may belong to the deeper architecture, not to any particular output. If the universe is an output, then it is not the final answer. It is an expression, a manifestation, a layer. This does not diminish its reality. Your computer screen is not less real because it is rendered. The emotions you feel reading words on a screen are not less real because the letters are pixels. Reality does not require fundamentality to be meaningful. In fact, this perspective may restore a sense of wonder that reductionism alone can drain away. The universe is not just a pile of particles in empty space. It is a coherent, self-consistent presentation of something deeper, something more abstract, something astonishingly fertile. The metaphor of an engine becomes useful here, not as a literal machine, but as an organizing idea. An engine takes rules and inputs and produces behavior. A reality engine would take informational constraints and produce worlds. Beyond spacetime, then, may lie not a void, but an engine, not a place, but a system, not a realm, but an architecture. And this architecture may not privilege any particular universe. Our universe may be one stable output among many. Other outputs may exist, or may have existed, or may be possible in principle. Some may be short-lived. Some may be sterile. Some may be rich beyond our imagination. This view also dissolves a lingering confusion about beginnings. If the universe is an output, then asking what happened before the Big Bang is like asking what happened before a program started running. The answer depends on the system, not on the output. The Big Bang may be the moment space-time appears, not the moment reality begins. Similarly, asking what lies outside the universe may be the wrong question. There may be no outside in a spatial sense. There is only a deeper layer in a descriptive sense. This also reframes the role of science itself. Science has not been wrong. It has been reading the right rules at the wrong layer. General relativity reads the geometry of the interface. Quantum mechanics reads the statistics of rendered outcomes. Cosmology reads the history of the display. Each is correct within its domain. The paradoxes arise when we mistake the interface for the engine. Once you accept that, many tensions soften. The incompatibility of quantum mechanics and gravity becomes a clue, not a failure. The vacuum energy problem becomes a signpost. Dark matter and dark energy become hints of sectors not rendered for us. The observer problem becomes a feature of how outputs are experienced. The universe stops being the ultimate object of explanation and becomes something even more interesting, a window. And here, something quietly profound happens. The question shifts. We stop asking what the universe is made of, and we start asking how reality is generated at all. What kinds of informational architectures are possible? What principles govern them? Why is there a rule space rather than nothing? Why does anything render? These questions are not yet physics in the traditional sense, but they may be physics in the making. Just as atoms were once philosophy and fields were once speculation, the architecture beyond space-time may be tomorrow's science. And, this does not mean we abandon equations or experiments. It means we widen the frame. We look for patterns that transcend space-time. We look for principles that explain why space-time works as well as it does, rather than just how. Perhaps the deepest mistake we ever made was not believing the universe is strange, but believing it is fundamental. Perhaps the universe is beautiful precisely because it is an output, because it is a story told by deeper rules in a language we are only beginning to decipher. And if that is true, then the end of this series is not an ending at all. It is a threshold, a moment where we stop mistaking the map for the territory, the interface for the engine, the universe for reality itself. Beyond space-time may not be darkness. It may be clarity of a different kind, a level where questions about origin, causality, and existence are not erased, but reframed. And standing here, at the edge of what we can currently articulate, we are reminded of something both humbling and exhilarating. Reality is not obligated to fit inside our intuitions, but it has invited us again and again to listen more carefully, to peel back layers, and to realize that what we see is not all there is. Not because the universe is hiding something from us, but because it is showing us exactly what it can, through an interface designed for beings like us. And perhaps the most honest thing science can say, at this point, is not that we have reached the end, but that we are finally beginning to ask the right kind of questions. And so, having stepped beyond space-time itself, having loosened even the idea of the universe as the ultimate container, we find ourselves in a strangely quiet place. Not empty, not resolved, but quiet in the way a deep ocean is quiet. The noise of familiar concepts has faded. Space, time, matter, cause, even universe. They are no longer foundations. They are expressions. And in that stillness, a different kind of question begins to form. Not what is reality made of, but why reality takes the form it does when it appears at all. This is where the conversation subtly changes tone. Up to now, we have been dismantling assumptions, pulling at threads, watching cherished ideas unravel into something deeper. But now, something constructive begins to emerge. A sense that beneath all these layers, there may be principles so simple, so abstract, that they do not resemble physics as we know it, and yet they give rise to all of it. If reality is generated rather than simply existing, then there must be generative principles, rules that do not live in time, but from which time arises, constraints that do not exist in space, but from which space unfolds. Not laws in the usual sense, because laws assume a universe in which they operate. These would be pre-laws, conditions of possibility. And, this is where humility becomes essential, because at this depth, language itself begins to struggle. We are trying to describe something that is not inside the world, but from which the world emerges. Every noun we reach for feels too concrete. Every verb assumes time. Every metaphor leaks. Still, we can gesture. Imagine a reality not built from things, but from consistency. A reality where what exists is whatever can exist without contradiction. Whatever patterns can hold together under their own rules. In such a framework, existence is not granted by creation. It is granted by coherence. This idea appears, quietly, in many places. In mathematics, structures exist because they are logically consistent. No one builds a number. No one manufactures a theorem. If the rules allow it, it exists timelessly. In this sense, mathematics is not invented. It is discovered. What if physical reality is similar? What if universes exist because they are internally consistent informational structures, not because something made them, but because nothing forbids them? In that case, the deepest question shifts again, not why there is something rather than nothing, but why consistency exists at all, why there is a rule space, why there is a difference between possible and impossible. This is an unsettling place to stand because it removes the comfort of cause entirely. There may be no reason in the usual sense, no prior event, no deeper mechanism, just necessity of a different kind, logical necessity rather than causal necessity. And perhaps that is why physics keeps circling mathematics without ever fully merging with it. Mathematics feels eternal, physics feels contingent. But if physics is an emergent rendering of mathematical consistency, then that tension dissolves. The universe becomes a particular solution to an abstract problem. This does not mean the universe is merely mathematical. It means that mathematics may be the closest language we have to describing the architecture beneath space-time. a language of relationships without substance, of structure without location. If this is true, then the reality engine we hinted at earlier is not a machine. It is a logical framework, a space of allowed structures, a realm where consistency determines existence. Within that realm, many possible universes may exist, some trivial, some chaotic, some sterile, some rich enough to give rise to observers who ask questions. Our universe may be one of the latter, not because it was chosen, but because it is stable and expressive. And, this perspective is strangely calming. It removes the pressure of purpose. The universe does not need a reason to exist. It exists because it can. This also reframes the idea of explanation. At some point, explanation does not mean tracing causes backward. It means recognizing necessity. You do not ask why 2 + 2 = 4. You recognize that it must. Perhaps reality, at its deepest level, is like that. But then another thought creeps in, softly but insistently. If reality is grounded in consistency, and if information is the substrate, then observers like us are not accidental byproducts. They are structures that consistency allows, patterns that can reflect upon themselves. Self-reference becomes important here. In logic, self-reference is dangerous. It produces paradox. But handled carefully, it produces richness. Systems capable of representing themselves within themselves gain extraordinary power. They can adapt, they can learn, they can wonder. Conscious observers may be precisely such structures, informational patterns that not only exist but contain representations of existence. Reality folded back on itself. This does not elevate consciousness above physics. It embeds it within the same framework. Consciousness becomes a special kind of informational loop, a pattern that persists by modeling both the world and itself within that world. And if observers are self-referential informational structures, then the universe does something remarkable when observers arise. It becomes aware of its own structure, not globally, not completely, but locally, partially, imperfectly. This is not mysticism. It is a statement about information flow. A system capable of representing its own rules gains a new layer of behavior. It can explore the space of possibilities. It can ask not just what is, but what could be. In that sense, science itself becomes part of the universe's unfolding, not a detached activity, but an internal process, the universe investigating its own interface. When we build equations, we are not standing outside reality decoding it. We are reality generating compressed descriptions of itself. Models are informational structures that mirror other informational structures. Understanding is resonance. And this brings us to a quiet, almost tender realization. The questions we ask are not arbitrary. They arise because the universe, through us, has reached a level of complexity where such questions are possible. The drive to understand origins, foundations, meaning is not imposed on the universe from outside. It is an emergent feature of the universe reaching a certain informational density. And perhaps that is why the deepest questions feel so personal, why they stir emotion, why they provoke awe. We are not just studying reality. We are expressions of it, trying to see beyond our own interface. This also reframes the idea of limits. We often worry that there may be questions science can never answer, that there may be a final wall. But limits may not be walls. They may be horizons created by our interface. A fish cannot see water because water is the medium of its perception. We may not be able to see the deepest layer of reality because it is the medium of ours. But we can infer it. We can feel its constraints. We can detect its shadows. Dark matter, dark energy, quantum randomness, fine-tuning, consciousness. These may not be separate mysteries. They may be symptoms of interface boundaries, places where the rendering shows its seams. And, once you see seams, you can no longer pretend the garment is seamless. But this does not diminish wonder. It deepens it. Because the universe becomes not a finished object, but an ongoing expression of deeper principles, a living structure in the most abstract sense. So where does this leave us? not with answers, but with orientation. We are not at the center of the universe. We are not outside it either. We are patterns within a pattern, interfaces within an architecture, observers within a rendering. The universe may not be fundamental, but our experience of it is real. Meaning does not require ultimacy. Beauty does not require finality. A song does not need to be the universe to matter. And perhaps the greatest mistake would be to think that stepping beyond space-time strips the universe of significance. On the contrary, it situates it within something even more astonishing. A framework where existence is allowed, where patterns flourish, where information can become matter, matter can become life, and life can become understanding. And standing here at this depth, another realization begins to glow. If reality is layered, if interfaces sit atop deeper architectures, then our current understanding is itself an interface. A provisional one, useful, powerful, but incomplete. Which means there is more to uncover. Not necessarily by going smaller or farther, but by thinking differently. By letting go of categories that once served us well, but now constrain us. By learning to speak in a new grammar of reality, one that is comfortable without space, without time, without cause. And so the journey does not end here. It pauses, it breathes, it waits. Because beyond this point lies a question even more delicate than origin or existence. A question about value, about meaning, about why understanding itself feels worthwhile in a universe that does not owe us answers. And that question, quietly waiting, will be the one we turn toward next.